Hello, beautiful people. So we're going to go through a couple more of these complex numbers in polar form questions, but we're going to go through a couple of examples of some more complex familiar type questions. So this one here is complex familiar because what you're going to be doing is you're going to be using polar arithmetic. So basically, you're going to be using a whole bunch of algebra and you're going to be using a whole bunch of letters and numbers. So let's start off by proving this identity. So the first thing I'm going to do is I'm going to define each of these, and I'm going to define them again just using values. So do you want to do A and B? Yeah, let's do A and B. So Z1 is going to be equal to A plus BI, and then Z2 is going to be C plus DI. So we've got to prove that if I add the conjugates, then it's going to be the same as the sum of the values, which then form a conjugate. That's not worded well. I'm sorry. I'm a maths teacher. I'm not a word teacher. Okay, so let's then write the conjugates of each of these. So the conjugate of Z1 is going to be A minus BI, and the conjugate of Z2 is going to be C minus DI. Okay, so if I add each of these conjugates together, so Z1 plus Z2, that's going to be equal to A minus BI plus C minus DI. And then I'm going to collect my real parts and my imaginary parts, and that's going to give me A plus C minus, just going to factor out that I, B plus D. And because I factored out the negative one here, that's why that's changed to a positive. So now what I want to try and do is I want to try and prove that's also true using this information here. So again, I'm just going to pop little brackets around them. Okay, so let's start off by doing Z1 plus Z2. So that's going to be A plus BI plus C plus DI. And again, I'm just going to collect my real bits and my imaginary bits. So I'm going to get A plus C, and that's my real bit. And then I'm going to factorize out that I, and I'm going to get B plus D. Okay, and so now the conjugate of that particular function is going to be, all I'm going to do is just change this symbol in the middle here to get A plus C minus I, B plus D. And as you can see, my left-hand side of my equation is equal to my right-hand side of the equation, and therefore the identity, the conjugate of Z1 plus the conjugate of Z2 is equal to the conjugate of the sum of those complex numbers. Gosh, that was a mouthful. Actually not a super tricky question, but because it's more theoretical or more abstract, it's a lot harder, I think, for people to get as opposed to something that's like more concrete or more measurable. Okay, so the other question that someone asked me about was question 19. So let's have a look here. I'm just going to make this a little bigger. I might start off with question 19a and then we'll move into question 19b. So we've got two complex numbers here. So determine what happens when we multiply those two complex numbers, working with both numbers in Cartesian form. So I'm just quickly going to write these in Cartesian form, and I showed you how to do this in the last video using the graphics calculator. So I'm just going to pop those two up there. Okay, so I'll just show you quickly what I did. I just went to my calculator, my real life calculator, and I just typed in those values. So this is currently in the polar form for complex numbers. I want to get it into the Cartesian form. So I'm going to go Shift, Menu, and I'm just going to scroll down to complex mode, and I want it in Cartesian form. So I'm going to hit execute there. So for the second one, what was it? Root 2. So if we go Shift, Root 2, Sys, oops, I don't want the Sys in there. Let's try that again, shall we? Sys, what was it, pi on 4. I've got it written here in front of me, so no, I'm not magically suddenly remembering this. My brain is not that capable. Okay, so let's close that bracket there and hit enter, and then that's how I got the Cartesian form for that particular solution, excuse me. So let's jump over here now. So this one here was already in Cartesian form, luckily for us, and we've got the x and the y coordinates if we were to plot this on an Argand plane. And then I just showed you how I got this into Cartesian form using that graphics calculator. So since we're multiplying these in Cartesian form, I'm going to write this as root 3 over 4 minus I over 4 multiplied by 1 plus I. And then I'm just going to use, some people call this the German handshake method, so you make sure everyone shakes hands with everyone else. I use FOIL, or so first, outside, inside, last, so whatever method. So we're just going to expand that. So this is going to become root 3 over 4 plus root 3 over 4i minus I over 4. And then this is going to be minus I squared over 4. Okay, so let's collect our imaginary parts and our real parts together now. Whoops, I just realized I did something silly. Because remember, when we have I squared, that's going to change into -1. So negative, -1, this value is actually going to change to positive 1/4. So the real parts are going to become root 3 plus 1 over 4 plus the imaginary parts. So root 3 over 4 minus 1 over 4 is going to be root 3 minus 1 over 4i. So that would be the multiple in Cartesian form. So what we can actually do, we can double check that using our graphics calculator. So let me just grab that question up again. So what was that? So we have root 3 over 4 minus 1 over 4i. And just as a reminder, to get to that I, we're going to go into option complex, and that's our little I there. And then we're going to multiply that by our other value, which was 1 plus I. So if we go back into option complex I. So if I chuck that in my calculator, what do I get? Yep, so root 3 plus 1 over 4 root 3 minus, I can't talk. You can see the answer. It's on the screen. It's there. We got the correct answer. Happy days. Okay, so next, determine UV working with both numbers in polar form and give your answers in polar form. So for this one, what we're going to have to do is we're going to have to convert that first equation into polar form because it's not currently in polar form. So again, we can just do this using our graphics calculator. So let's go back into our calculator. Now this time what we want to do is we want to have them both into polar form. So let's change that into complex polar form. So if we go shift, setup, and then we scroll down, and we're going to change this to polar form for the complex mode. Okay, so let's substitute those numbers in now. So we had root 3 over 4, and then the imaginary component was minus 1 over 4i. So again, to get that I, we just went into that complex mode. So there's I there. Okay, and so that's my solution there for the polar form of that number. So let's go ahead now and let's write those two values in. Oops, excuse me. So we have the first one. The first one was U is equal to 1/2 cis negative pi on 6 for our first one, and then the second was V is equal to root 2 cis pi on 4. Okay, so let's do this now using our multiplication. So we're going to go U times by V. So that's going to be 1/2 cis negative pi on 6 times by root 2 cis pi on 4. So remember, when we're doing this in polar form, we're going to use that little multiplication theorem. So if I have two polar numbers multiplied together and they're in polar form, then I'm going to multiply the two values at the front. So that's going to be R1 times by R2 cis, and then I'm going to add the angles there. Now, if I was dividing, I wouldn't be multiplying these, I'd be dividing these, and then I'd be subtracting the angles from each other. So we're going to have root 2 over 2 cis, and then I'm going to add these two angles together. So I'm just going to pop that in my calculator. So negative 1 over 6 plus 1 over 4, and that's going to be equal to 1 over 12 pi. And again, I can just chuck this now into my, oh wait, no, hold on, never mind, because it wants it in polar form, doesn't it? Yep, so that's it. So that's all we have to do to get it, our answer in polar form. Okay, so moving on now. Hence, deduce the exact value of sine pi on 12. So let's clear all this stuff up, and then I'm going to come back and show you the solution. Okay, this is about to get ugly. So I've gone through and I've had a quick look at the textbook because I wasn't sure if this was a tech active or a tech free question. Because if it's a tech active question, it's really simple, because all you're going to do is you're just going to chuck that into your calculator and you're going to get your solution, which is root 6 minus root 2 over 4. But I'm pretty sure, according to your textbook, this is actually a tech-free question. So I'm going to show you how to do this without using a calculator. So we're going to need a couple of pieces of information. We're going to need to use our special triangles, and we're going to need to use our trig identity. So when we had a look at that last one, so just going to refresh. So using that formula, if we are multiplying two numbers together and they are complex numbers in polar form, then that's the same as multiplying their two modulus values and then adding the two angles there. So for this one, I think it's just effectively saying that this R value at the front is going to be equal to 1. Now we could rewrite this particular angle in here, right? Because we had our two angles before. So our angle 1 was equal to negative pi on 6, and that's the same as 30 degrees. And I'm going to work in degrees for this just because I think it's going to make it a little bit easier for me, and then I'll convert back to radians if I need to at the end. Okay, and then what was our other angle? Our other angle was positive pi over 4. Okay, and positive pi over 4, if we were to convert that to degrees, that's the same as saying 45 degrees. Sorry, this should actually be negative 30. So if I rewrite this now, I can rewrite this as, because the values of R are just 1, so I'm just going to write this as cis angle 1 plus angle 2. Okay, so that means that I can actually separate this out. So I'm going to write this as sine of angle negative 30 degrees plus 45 degrees. And because I've written in this form, I'm actually going to have to use one of my trig identities. So if I want to find an angle, and let's say we've got x plus y, then we're going to use our trig identity. I've written it down here. Where did I write it? Here we go. So that's going to be equal to sine of x times by cos of y, and then we're going to flip that, plus cos of x sine of y. All right, so the next thing I'm going to do is I'm going to substitute in my values. So sine of negative 30 degrees plus 45 degrees is going to be equal to sine of negative 30 times by cos of 45 plus cos of 45, so the reverse now, sine of negative 30. Oh, squishy. Okay. So this is where our special triangles are going to come in. I'm going to just quickly draw them over here. So we've got two special triangles. The first one starts off as an isosceles triangle. So this is our 45, 45, 90 triangle. And the other one is also an isosceles, but it's a slightly different isosceles triangle. Oh my gosh. There we go. And that is our 60 or 30, 60, 90 triangle. So what are the lengths along here? The length along there is going to be 1, the length along there is going to be 2, and the length along there is going to be root 3. So since this is a tech-free question, I think you can kind of see why this is a more complex example. So we are going to substitute in the values that we do know. So if I have sine of negative 30, and again, I'm also going to bring up my car circle real quick. So that's going to be there. So in this particular quadrant, sine of negative 30 is going to be a negative value as well. So let's have a look here. So sine is going to be my opposite over my hypotenuse. So that's going to be negative 1/2. Cos of 45, so cos is going to be the adjacent over the hypotenuse, so times by 1 over root 2. And then same thing now for this one, so cos of 45 is going to be the adjacent over the hypotenuse, so that's going to be 1 over root 2, times by sine of, oh, sorry, that should be the opposite way around. Let me fix that. I'm just going to pause one second. Okay, sorry, I messed that little section up there. So this should have been sine 45 and cos negative 30. I had written this twice, so that was a bit stupid, so I apologize for that. So sine of 45 is going to be the opposite over the hypotenuse, which is also going to be 1 over root 2. And then cos of negative 30. Now in this particular axis, cos is still positive. So this is going to be times by positive root 3 over 2. So if we look at cos, it's going to be the adjacent over the hypotenuse. Now I'm just going to quickly fix this by rewriting this in its rational form. So that's going to be root 2 over 2. And same thing with this one here. Oh, sorry, wrong way around then. Doing well today. Root 2 over 2. Okay, so now let's find this solution. So negative 1/2 times by this is going to make negative root 2 over 4 plus root 6 over 4. So if we rewrite that, we can rewrite that as 6 minus root 2 over 4. So if we were to just pop this in our calculator as a tech-free question, this is actually a pretty simple question to do tech-active. It's really, really quite tricky without the calculator. Okay, so this last question here, so using the formula sine x minus y, verify your exact value for sine pi 12. I'm not going to go ahead and do that. I want to move on and I want to have a look at this next question here, because question 19b was the one that I had a specific question about from a student. So I'm going to clear all that. I don't think I need to show you how to multiply things in Cartesian form and polar form again, but I will show you how to do another example using trig identities. Okay, so again, this is a really simple problem if we are doing this with the calculator, because we can just chuck the value in there, but let's try and do this as a tech-free question. Okay, so I've written my trig identity here, I've got my triangles just here, and I've written out the angles. So all I've done is I've just converted this into polar form and I've just taken the angle there. So that was the angle from that particular question. This one here already had the angle of, oops, sorry, that's the wrong angle. Doing well. Okay, so let's try that again. So that's going to be the angle 2 pi on 3. Okay, so let's rewrite this using our trig identities. Just going to quickly substitute these values in and I will come back. 2 seconds. So I've just filled out that formula there. So now what I can do is I can go back and I can use these triangles. So sine pi on 4. So let's use our car circle just quickly here. So if I do sine pi on 4, that's the same as saying negative 45 degrees. And in this quadrant, sine is actually going to be negative. So if we have a look, sine is going to be 1 over root 2, which is the same as root 2 over 2, and it's negative in that quadrant, multiplied by cos 2 pi on 3. So if we look at the angle 2 pi on 3, right, that angle there is going to be 2 pi on 3, but this little angle in here is going to be pi on 3, which is the same as 60 degrees. So we're going to do cos of 60 degrees, so that's going to be the adjacent over the hypotenuse, so times by 1/2. And also this is positive in this quadrant, so I'm just going to keep that as positive 1/2. All right, same thing now. Oh, sorry, that was wrong. Cos is negative in that quadrant, sine's positive still in that quadrant. So let's fix that up. And let's put this value here. So sine of sine of 60 degrees is going to be the opposite over the hypotenuse. And that one will be positive because sine is positive in this quadrant. Times by cos negative pi on 4. Now again, cos is going to be positive in this quadrant. So cos of 45 degrees is going to be root 2 over 2. So if I do that multiplication now, let's actually pop this down here. This is going to make root 2 over 4 plus root 6 over 4. So that should be root 2 plus root 6 over 4. So let's just quickly double check that by popping that into our calculator. So if we put in sine 5, where's pi? Shift pi over 12. Then we are going to get square root of 6 plus square root of 2 over 4. So that's good. So our solution has worked. So this is why it's a complex question, because it really is, because we have to use those trigonomic identities. It's not tricky at all if this was tech active. All right, so I hope that's answered some questions. I think the answer in the textbook actually might be incorrect for that one. Anyway, Miss Cameron says I need to come up with like a proper goodbye. So maybe you guys can give me some ideas about how I should say see you later to everybody. Well, see you.